Hello everybody. This is our second problem solving session and we are starting transmission lines. I'd like to first clarify why I'm teaching transmission lines before all the electromagnetic subjects, which are mainly physics 2 subjects. So number one reason is transmission line is one of the applications of all the electromagnetic topics, but it doesn't directly depend on those topics. Those topics can be used to explain the theory behind transmission line, but the analysis of transmission line, we don't really need those. So I'd like you to see the application first and not think all in the time of learning the electromagnetic topics that these are really unused things. So second of all, I choose transmission lines because, like I said, the analysis of transmission line doesn't really depend on the electromagnetic engineering course topics, so we'll just use our circuit theory. And then the third reason is transmission lines are heavy math, and chapter 7 is also heavy math, but I like to keep the heavy math stuff in the beginning while you're still 100% interested in this course. Okay, so here are some kinds of transmission lines. Transmission lines are just like any line, any electrical line which we use to transport electricity is used to transport electrical energy, but it does it by the means of electromagnetic waves propagating on it, so it's also a guideline for electromagnetic waves, although it's wired. So one example is a coax. Basically, all the transmission lines are two conductor, one insulator. So coax is a cylindrical outer conductor and an inner conductor and an insulator. And then we could have two parallel wire ones, and then we have microstrip lines, and then we might have an unbalanced line. Okay. So how can we calculate the effect of transmission line, or how can we calculate if a transmission line is affecting our transporting of energy, if we need to count the effects of transmission line. So the basic idea is, if your transmission line is long enough, longer than in a certain amount of more than your wavelength, then you definitely need to count the effect of transmission line. Even if you don't count, they are there. So for your calculations to be precise, you need to count them. So here's an example to explain the role of that length, or how we can derive that proportion of transmission line in the wavelength. Let's say we apply some potential at this point A and at this point B. So let's say, since we're applying AC potential, the potential at point B is V naught cosine omega t, and then the potential at point B is of course delayed, and the delaying amount is the length divided by speed. This is basically the distance divided by velocity, right? Let's compare them at some time, so we need to set some time. Let's say our applied potential is on 1 kilohertz, and we can calculate our omega, and then let's say the length of the transmission line is only 5 meters. So, and then let's plug in t is equal to 0, and then let's see the effect. The potential measured at B is 0.99 of potential measured A. So this is not really a big effect, but let's take a look at when we have a longer transmission line. Let's set our length to 20 kilometers, still at 1 kilohertz. Then the potential at point B would be 0.91, so there's almost like 9% of attenuation in the magnitude of potential. So this is an effect by transmission line, and we cannot ignore this. So if we just calculate this delay, because it's cosine of that delay, and delay is omega L over C, and if we plug into pi f for omega and then L over C, and we know C is the propagation speed, which is also frequency multiplied by wavelength. So if we plug in for C that amount, then we'll have 2 pi L over lambda. And then if this number is less than 0.01, which means cosine 0 is very close to 1, that means we don't have much attenuation affecting, we can call this line non-effective. So the length of this line is not effective enough. And then, but if that's more than that ratio, then we can say that this transmission line is affecting our calculations. Okay? So here's an example from your book, 2.1. Basically, this question is just giving you cases where you can just calculate if we can ignore the transmission line or not ignore the transmission line. I'm just going to look at A and C. And this is an airline, air-filled transmission line, meaning that the insulator is air. So that means the wave propagating on this transmission line, whether the electromagnetic wave or you're gonna see the potential and current as a propagating wave later. Then those have a propagation speed of c, which is the speed of light. So that's 3 × 10⁸. Let's do our calculations. For length 20 centimeter, frequency is given as 20 kilohertz. If it is air-filled, then UP is 3 × 10⁸ meter per second. We'll just simply plug in and find the wavelength of this, again, potential or current wave. And then if you calculate that ratio, we find 1.33 × 10⁵, which is really small compared to 0.01. So we don't really need to account for the effects of this transmission line. So that means this connection is non-effective. But let's say we have the same length, but a larger frequency. This is almost a gigahertz, 6 gigahertz, still an airline. So let's do the calculations for this one. Lambda is 0.5 meter. And then the ratio is almost 410 to the -2, which is around 4, which is really big compared to 0.01. So that means we cannot ignore the effects of this connection. So even the length is really the same and short, which is 20 centimeter. When we increase the frequency, we really need to account for the effects of our transmission line. You don't even need to call this transmission line. This is really a connection. But since it becomes effective, it may look like a transmission line. And the second problem I have today is 2.5. So we have a parallel plate transmission line, and then line parameters are given by these numbers. Just keep in mind that this is not ohm, this is ohm per meter, Henry per meter, farad. These are all distributed elements. These are elements per length. So let's say, let's practice calculating the constants. The first one is attenuation constant. Second is the propagation phase constant. Third one is the propagation velocity. Z0 is the characteristics of the transmission line. And all of these we're going to calculate at 1 gigahertz. The frequency of applied voltage really changes many of these constants. So here is our features of transmission line. And then I have a little picture here to explain what a propagation speed means. Let's say that there's a surfer and it's traveling on an ocean wave, and let's say the surfer is here at some time, and then 10 seconds later it's here. Let's say the wave carried the ocean 2 meters in 10 seconds, and then UP of this wave will be 2 divided by 10, which is 0.2 meter per second. Let's come back to this problem. To calculate, we need to calculate our omega, which is 2 pi f, so it's there. And then these are primes because those are the resistance or inductance of distributed elements, not the whole thing, but distributed elements. So we just plug in numbers. Now, a couple of advice on working with complex numbers. If you're multiplying them, I advise you to turn them into polar. Or if you're taking the power of them, again, I advise you to turn them into power. So you can just calculate the polar of these two and then multiply and take the power, 0.50 power, right? So if you do that, here is what you get here. Well, in this one, I just multiply by distributing, but you don't need to do it like that. You can turn that into polar. So I have everything in terms of polar representation. It's really easy to take the power of that. We just take the power of the magnitude, and then we take the power of the angle. So I need to take the square root of 1154, and I also need to divide this almost 180 to 2. So I'll get 34e to the j, but I really need to put this in rectangular form because if you look at the gamma, which is called propagation constant, basically is alpha plus j beta. So to see what alpha and beta is, I need to turn that into rectangular form. And I can see here that alpha is 0.016 Nepere per meter, and beta is 34 radians per meter. And I can plug in those in the formulations. I can calculate the propagation speed, and that's almost half of the speed of light. Again, plugging in the formulations, I can calculate the characteristic impedance. So you can see the characteristic impedance only is affected from this distributed elements and then also the frequency. So this is the characteristic impedance, and it's very natural for characteristic impedance. These are also called complex impedance of a transmission line to be a complex number. Okay, this is the end of 2.1 problem solving session. If you have any questions, you can email me or we can virtually meet. See you in the next week.